Thank you, Norm. At this point, I will invite our panelists to take their seats up on stage so that we can grill them. And also, if you have questions that you've written down on those note cards that hopefully looks like many people have, please pass them down to the aisle and we will collect those.
So now we have light.
And if there are people who are standing in the back and who would like to rest, we now have free seats up in the front that are theirs for the taking. So while we're collecting those questions, I'm just going to ask a generic question of all our panelists. In their perspective, with regards to both natural hazards and our level of preparedness, in what respects is California in a better position, and in what ways is California worse off than Japan? And I'll let anyone who wants to take that. Hopefully the mics on the table are on.
I mean, just from a hazard perspective, I think Japan and California are very similar, and as best as I know, the preparedness is quite comparable as well. Japan and California always sort of presented as sort of being the ideal case as to how far preparedness has been pushed, but as we just learned, even that is not to imply that we're safe. A big earthquake here in the Bay Area will be catastrophic, will be a real problem, but it will not come close to what we've seen in Haiti and some other places that we're not able to prepare to the level that we can here.
I'll make one, do I have to push the button? One general comment I think that distinguishes Japan and the U.S. and having tried to work with the Japanese for a while on critical structures, the key to me is that in the U.S. we tend to treat things or address risk more directly. We actually look at beyond, as I said there, beyond design basis, what can go wrong and so forth. The Japanese in the past have been much more on a simple deterministic basis. This is our design. If I meet it, I'm good, without seeing what if we're wrong, what if something bigger happens. And I think that's, in my view, the key cultural difference.
I would just echo on the nuclear side, that's also the case in terms of how the infrastructure is regulated.
So the Japanese tend to be far more empirical in their basis, and the United States tends to be more scientific and analytical and probabilistic in our approach to problem solving. On the Japanese side, they also have one country where the entire nation is subject, perhaps weekly or certainly monthly, to earthquakes, and so there's sort of a national policy that earthquakes are a problem. And if you go to Washington, D.C., there's a sense that, well, earthquakes are only a California problem, and there's only 2 state senators, so the traction that you get may not be as much or as important as we think it might be. The Japanese have also reacted very strongly when there is something that they don't expect. So after the Kobe earthquake, they did put in something like 1,000 strong motion instrument records throughout the country, which then you can read in real time immediately following an earthquake, except the server center was damaged in the earthquake and it was delayed for a couple of days. And they built the world's largest shaking table. It can test full-size 7 or 8 story buildings on the shaking table to demonstrate that things will work or they won't work, and we haven't quite gotten there yet.
In terms of tsunami preparedness for the general public, I think the Japanese are much more tsunami education than we have. They have a different problem, though. Their tsunamis come in as little as 3 minutes, where we have hours. But just in our last tsunami, to see surfers off Santa Cruz during a tsunami warning is a little distressing. I don't think you would see that in Japan.
I would say that echoing what Steve was saying, is that the Japanese are better prepared in terms of seismic and geodetic recording capabilities, but it's something that we in California are working to improve upon. The flip side of the coin is that we're maybe better off in that the seismicity rates are lower here, and the degree of our exposure is lower.
So there's a question here that I think many people were asking. This is phrased with a degree of incredulity. In 1906, apparently, according to the questioner, Chile had an earthquake that was a month apart from the San Francisco quake, and similar to the recent combination of the earthquakes in Chile, Sumatra, and the Sendai quake. And the questioner says, and you say they are not linked. How do we know they're not linked? Is there some physics behind how stress propagates through a plate, say, that would tell us that?
Well, there are 2 points. You can look at it either from a physics point of view, and if you model the stresses from one earthquake, how far they reach. They just do not reach to significant levels further than about 2 times the size of the earthquake rupture. The other way you can look at it is empirically. You really look at good data, and there was just a paper published 2 days ago in Nature Geoscience by Parsons and Velasco. They looked at all the earthquake greater than magnitude 7 in the last 30 years and looked at did they trigger earthquake elsewhere in the world, smaller earthquakes and bigger earthquakes. And they found actually less earthquake triggering to occur, essentially none at those levels, than you would expect based on the little ones that have been shown to get triggered globally. So if you take all the earthquakes that were ranging from magnitude 7 to 8, actually 9 globally in the last 30 years, none of them have triggered large earthquake elsewhere in the world. That's sort of the current state of knowledge.
So a question here that I think is probably best pitched to Doug and Eric. If there were a large Cascadia subduction zone quake causing a tsunami to reach the Bay Area, the questioner asks, how long would it take to get here? Would there be enough time to warn people and evacuate them from tsunami inundation zones?
Looking at my travel time map, I think it's about an hour to get here. It's our closest big, I think it's about an hour. I think it's our closest big earthquake rupture zone that could generate a tsunami. There's a lot of disagreement on how large the amplitudes are going to be. It's a very complex wave that comes down the coast. It's a trapped wave, similar to surface waves in seismology. They're very difficult to model. Some people don't think it's going to be a big problem. Other people think it might be worth looking at. But that's a future area that I think we need to pin down a little bit better.
The other part of that question was how do we affect efficient evacuations or response to that tsunami threat? And I think probably the most important thing that we could do is improving education on what people should do once a tsunami alert has been issued, and not fall back on a reliance for what public officials are going to be instructing people at the time of the disaster. But there needs to be preparation beforehand, some knowledge on what to do once that information is released.
Just one point, I was told that the viewers in the other room, we have people in a spillover room who are watching, so people could just speak up so that their voices will be captured on the microphone, and that way they will be able to hear. I'm going to try to pick questions where I can at first just move down the table. So, Stephen, this one is a personal question from someone in the audience. I have a one-story 1923 stucco home with a new foundation. How much damage is likely to such a home in a huge quake?
I think Norm, showed that there's just a factor of, for a given earthquake at the same distance from the fault, there's a factor of 10 difference in the intensity of shaking, and there's a certain amount of luck or location. The thing in real estate is location, 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 and it's the same thing in real estate and earthquakes. Some of the older buildings that are well built, that are tied to foundations, may likely respond better than some new structures. Some of the buildings from the 1906 earthquake stood up quite well, and some buildings designed after the Second World War are not intended to be quite as safe. As far as checklists, many older buildings aren't tied to the foundation, so there's anchor bolts that are normally provided if you have a concrete foundation to the sill plates and to the upper part of the structure. There's something called Plan Set A or B, depending on what your situation is. That is how you can go down to Orchard Supply and Home Depot and buy material to retrofit your house so it's tied to the foundation. I understand the California Earthquake Authority will give you a discount soon if you do that to your house. There are things like chimneys that are oftentimes falling hazards in older homes, and they could fall onto the roof and into your dining room table or away from the house into the street. And then some of the worst of the buildings are your irregular ranch-style houses that are just full of windows and irregular shapes that aren't tied together well. So you need to hire an engineer, not me, to evaluate your house.
That's right. Get an engineer. Don't rely on the advice from this panel discussion. So move on to Norman. Another personal question. How safe is the BART tunnel under the bay? What is the likelihood of surviving the big one if you're on the train at the time? And let me just add an element to that. In your slides, you said there, you're giving probabilities of 1 in 1,000, 1 year in 1,000, something bad happens. But by that, do you mean total catastrophic failure of the piece of infrastructure, or that it's damaged? Can you?
Sure. So the numbers that I had in that table were not a chance of damage. That's the chance of the ground. That's the level of shaking that we set. So how strong do we want to? What's the strongest shaking we want to consider in the design? And so we take a shaking level that has, let's say, a 1 in 1,000 chance of being exceeded. Once you've done that, there's a whole issue then of what is the capacity of the structure to withstand even beyond that design basis. And so the probabilities of catastrophic failure should be much lower than the for example, 1 in 1,000. The BART tube is a very difficult situation. I will be careful what I say here, but it's a difficult thing to retrofit. Okay, so I think that some of the basic issues they've had is the tubes being, during an earthquake, starting to float, and if it floats up, it can open up and then water can come in. So how do you staple the tube down? And that's a very difficult issue. So BART has been working on that and have made the retrofits they can, but I'll see if I ever work for BART again after this, but they've, an issue we have in these types of things is when you go to the public and ask for money, the first time they asked, they were turned down. How much do you tell the public of risk? How much do you scare people in order to free up funding versus losing all your riders because they're all too afraid to go? So but that tube is a very difficult situation to really fix. That may be one of those things down the line where you rebuild it. That could be the long-term solution to that problem.
I think this is also an illustration of, bad things can happen. That the tsunami is 5 meters taller than they designed for, or something like that. So rare events do happen, and so there are things, not just the BART tube, but where they have other consequences. So in the case of the BART tube, if there's a breach, it's not good for the passengers on a particular BART train. But much of downtown San Francisco BART stations are below sea level, and many of those then have entryways into buildings. Those buildings then have chases that run into all the electrical conduits and telecommunications and internet systems that run most of the downtown San Francisco. So there's a cascading kind of infrastructure problem that you can have, but you can envision this if the water goes out or the electricity goes out or something else like this. So bad things can happen. They're very rare. And as Norm suggested, it's impossible to design for the worst case of every situation.
So this is a question here that I will ask of Per. How do we decide, paraphrasing the question, but how do we decide at what level to design, what level of hazardous event we design a power plant? And I've heard it mentioned that power plants are designed to only have a major core problem once every 10,000 years, so 1 in 10 to the 4. But if we have 300 plants in the world, then that probably means once every 30 years we're going to have a problem. Who decides what that number is? Is that just the number that's feasible, or are there other rationales that go into those types of odds?
But before he answers that, could I again straighten out, when we say 1 in 10,000 for a nuclear power plant, that's not a core damage. That's a shaking that has a 1 in 10,000 chance in a given year of happening. Beyond that is then the whole process of what the structure can take.
Right, and of course I could give an hour-long lecture on this topic, but I'll try to compress it down to just a couple of minutes. The key thing in trying to engineer systems is that we do want to use a risk-based approach, and that is the more modern approach to trying to assess their performance when they're challenged by external events and internal events like this. The issue when we apply these risk-based methods is that we have incomplete knowledge. And so when we look at systems that have the potential to have fairly high hazard associated with them, like nuclear systems, the other major element of the design is to introduce defense in depth. That is, that if your assumption about the plant shutting down safely and having emergency diesel generators turns out to have not been correct, then you should have some capacity to continue to provide cooling absent external power. If it turns out that your electrical switchgear has been devastated and the supplies of fresh water have been wiped out, and you cannot hook up your emergency diesel generators because the switch yards are torn apart, then you should have the capability to retain fission products as you severely damage fuel in a reactor inside a containment building. And then if you have material get out, you should have the capability to implement emergency response and move people away so that they are not directly exposed. And indeed, this is pretty much our first opportunity to work through deep into these layers of defense in depth. And interestingly enough, at this point, what we do know for sure is that there have been no radiation fatalities whatsoever from this accident. There's actually been, to my knowledge, no cases of radiation illness, which would emerge at substantively lower doses. The health authorities are monitoring for radiation exposures. The highest sensitivity is with exposure to radioiodine, and the uptake in children near Fukushima has been sufficiently small that it falls well within what the goals are for the protective actions. And in fact, at this point, absent further progression in terms of the severe accident phenomenology, it does appear that exposures are so low that there will be no statistically detectable changes in terms of people's health. There will be exposures, there will be additional cases of cancer based on our understanding of that, but they will be so small in number relative to the background that it will be impossible to detect them statistically. So that means that from the perspective of public health, the vast overwhelming consequence from the tsunami and earthquake is the direct impact on people, not the nuclear accident. Also, when we start to look at just the raw economics, in my estimation, the cost of cleaning up this accident will be somewhere on the order of about 1/10 of the total economic losses from this event. And so this is in a world, of course, where we're looking at the potential by the end of the century for things that could be substantively more damaging from the perspective of climate change. We're looking at public health consequences from the continued use of fossil fuel that clearly dwarf also these consequences. In general, it's going to take a few months to probably years to fully understand what has happened here. But thus far from those things that one should care about, the consequences have been surprisingly limited, mainly because of the defense in depth that comes from having containments that are effective in retaining a large amount of the radioactive material that was released in a Chernobyl type of accident, and then taking protective actions, including evacuations for the necessary period of time. Right now, the information we have on ground contamination is that it's far lower than what happened with Chernobyl. We still don't know about long-term land use restrictions in any detail, but chances are very slim that they'll be as extensive as what was required for Chernobyl. So that's sort of where things sit.
Just a,
Could I try to address one issue? I think part of that question was back to, instead of individual structure risks, portfolio risk, right? And we run into this problem in California. You have hundreds of dams. If you do each one to 1 in 1,000, doesn't that mean every 10 years you're going to have a failure, right? I mean, it all starts to build up. And that issue regulators are struggling with. This is part of the reason why dams in California are still done on a deterministic basis, to avoid, I think, recognizing and quantifying what that true risk is in the portfolio. On the nuclear side, what has really been done is to keep the acceptable risk on the nuclear side much lower than your acceptable risk on other things that we're doing. Okay, so your other aspects of life, dams, your bridges, and so forth. But there isn't a number that somebody in the end says, a regulator doesn't want to say, I'm willing to kill this many people with this much probability. And so they stay away from that part of it.
I'm sure everybody knows more about probability and statistics than I will ever know in this room. But oftentimes when you talk to people in the general public and you start talking about 500-year or probability of 1 in 500 or 1 in 1,000 or 1 in 2,500 years, they figure that, well, the last earthquake was in 1906. It's around 2006 plus a few years, so they can just defer thinking about this for another 400 years. Right. And the probability doesn't quite work that way. That it is a 1 chance in 500 years that we're looking for this earthquake being exceeded, but that corresponds in that case to a 10% probability of exceedance in 50 years. And so this is not your average earthquake that you would have over the life of a structure, but you would have a chance that 10% of the earthquakes might be larger than that number. And so you design for that. And then as Norm said, that's the earthquake that the engineers consider, but then you design a structure such that if you get up to these really large earthquakes, an earthquake with a 2% probability of exceedance in 50 years, it's still a 2% in 50 years of having this earthquake, you have a 90% confidence that your structure won't collapse. And so then the engineers on the engineering side work to achieve this probability of collapse. But that is probability of achieving life safety, not having collapse. It means if that earthquake happens, you may not get back in the building, but hopefully you can walk out of it and do something else another day.
So keeping on probabilities, just in terms of seismic risk, one of the members of the audience asked, which of the faults is most threatening right now? Is it the San Andreas? Is it the Hayward? Where do we expect to see the next big earthquake in California?
Well, based on the probability estimates, our fault wins. The Hayward fault has, here in the Bay Area, the highest number of occurrence, and that is based on what I quoted earlier. The time since the last earthquake in 1868 and the average recurrence interval, which is highly variable, but it averages about 140 years. So it is considered to be ready to go now, but it could also go in 30 or 40 years. The plus minus in the recurrence interval is 50 years. In California as a whole, the southernmost San Andreas fault, starting near Palm Springs and up towards LA, has an even higher estimate. Now the problem is there are so many faults, and most earthquakes that have occurred in recent history happen on faults that are not the main rapid players. There are many, many structures that can produce earthquakes, so there's always a background risk. But just probabilistically, here in the area, the Hayward fault is definitely right now number one.
Then following up on that, someone is asking, how will the Hayward fault rupture affect San Pablo Bay, and the Bay Area waterways?
Well, in terms of the tsunami, somebody might be able to answer about the engineering to the, like the levees, but in terms of the tsunami, probably very little, although the 1868 Hayward, there's some reports of actually landslides off the cliff house generating some local waves. We're also interested in what's called a step-over structure between the Hayward and the Rogers Creek. In 1896, I believe, there was something that looked under San Pablo Bay that looked like it was produced very small, but these are very small tsunamis. So the tsunami risk is pretty low. They're scientifically interesting, but it's pretty low. But I don't know if anybody wants.
So, Eric, you showed in your presentation a landslide generated tsunami that reached over 40 meters high in that animation. And just for perspective, that's about halfway up Sather Tower here on campus. Is that something that we're actually expecting to see in
No, it's a good question. That amplitude was right above the landslide, and that was a submarine landslide. And I didn't bring up the point that there's what we call subaerial landslides, or cliff failures, basically. These will generate some high waves very close to the cliff failure. So we had a cliff failure near Muscle Rock in 1906 that might have generated some waves. We have all these cliffs like in the Coquina Straits and elsewhere. They'll generate very localized waves, but nothing, I doubt, on the 40-meter realm. We're looking at, in that case, Puerto Rico, which has some amazingly steep slopes off the offshore Puerto Rico. But you can get, certainly in Alaska, you can get tsunami or waves that high from a landslide.
But offshore California, I mean, this is an issue for us. Your two nuclear power plants, and your shutdown one up at Humboldt, all have had tsunami studies done. And for both Diablo Canyon and San Onofre, the offshore landslide is the way you get the big wave. I mean, that's the biggest issue. The recurrence intervals are the difficult part. They appear to be on the order of 20,000 to 50,000 year recurrence intervals. So very rare, but big offshore landslides is what causes the large waves at those two locations.
Yeah, except we don't really have a lot of direct dating of a lot of these landslides in California. And off of Southern California, we do. We have some. You need to go out, take a ship, and get a core data and actually date the material surrounding the landslides. And unfortunately, we don't have a lot of that information, not only for California, but on the East Coast. There's some gigantic landslides off the East Coast. And we just don't have that data for those slides either.
So another question here that ties into this is asking, how do we predict big events like, say, the big earthquake in Japan when there's such a limited data set of these big events because they happen so infrequently? What is the science behind determining those recurrence rates? How does one go about doing that?
Well,
I've stumped the panel, so whoever asked that question.
Well, we can't even predict little earthquakes, but at least we have, a forecasting window. The really, really rare events.
Well, I mean probability. I mean, as opposed to predicting exactly when it happens.
Well, the rare event, the harder it is to have any meaningful estimate. But I think one should consider, there is the possibility of knowing that it happened at least once in the geologic record that you could have a bigger earthquake. In Japan, the earthquake history, the modern history, had been such that there hadn't been any earthquake as big as this one. And therefore, the seismic hazard map for Japan in that particular area was built on knowing that they're magnitude 7 to 7.5 type earthquakes, maybe a magnitude 8. But there was some knowledge that in 869, as Steve also mentioned, there was a tsunami-generating earthquake that may have been much bigger. So there was sort of this one piece of information that was not incorporated in the hazard estimates. And so that's the question, should we always, look at the worst case scenario, and then how do you assign a probability to an event that only happened once in very, very early history and was not very well understood?
But in practice, we do use geologic information to go back in time. So we don't rely very much on the historical data. It's slip rate data on faults from geologic information. or now more recently as well, geodetic information to tell you how strain rates are going. And we build models that should be capturing the behavior over tens of thousands of years so that we can extrapolate and predict these rare events that would happen and not ignore them just because they haven't happened in recorded history.
There's also, if you look at things probabilistically, Steve had put up a very useful diagram, which is the challenge versus the capacity of the system. In Japan, we had a previous earthquake that disrupted a power station at Kashiwazaki, and the magnitude of the earthquake and accelerations at the site exceeded the design basis. But the design basis is a point in this curve, and in fact, the capacity of the plants to accept the ground motion was such that they shut down safely and no safety-related equipment was damaged as a consequence. So I think one of the problems that you run into is that when you talk deterministically about this is the strength of earthquake that the plant is designed for, you create an incorrect perception that there's a cliff at that point. And furthermore, you incentivize engineers to ignore things that might go beyond that point and not think about how the system might fail, and therefore identify cliffs and design the system so that it is capable of failing in a graceful way. And for structural design, for example, for nuclear plants, the older practice was to design them to be fully elastic, extraordinarily stiff and strong, robust structures, which is fine from a deterministic perspective because you know that there is a threshold below which they will respond well. But we quit doing that for automobiles ages ago because it's much better to design systems to fail and crumple in a graceful way. And I think that you see a lot of these features introduced into the new plant designs that we have, and there's further opportunities. We face a social question, though, about old infrastructure, and it's not just old nuclear plants, it's Echeverry Hall. Frankly, it was built in 1967, before the 1972 changes in earthquake codes, and how it is we decide and invest to replace old infrastructure with better infrastructure is a big challenge. In the case of nuclear systems, we have old nuclear plants, but 50% of our electrical generation comes from old coal plants. And it is not an easy question which you want to retire first, but if you did it based purely on environmental and public health problems, you'd be shutting down the coal plants first, almost certainly, if you were to look at things in a careful way.
I'd just like to add that the recent Japan earthquake provides an opportunity to evaluate paleo seismologic data sets, so things like inundation zones. And it's an opportunity to go and look at places that subsided and look for evidence in the geologic past in terms of the stratigraphy for evidences of previous large subsidence events and tsunami deposits. And perhaps by doing that sort of analysis in Japan, then we could learn about what needs to be done to better characterize subduction zones around the world.
So I'll just ask one last question to wrap up. If there's essentially, if there's a take-home message you could leave us with, each of you, in terms of what we could be doing to prepare. Maybe this is something that we are already doing, we need to redouble our efforts on. Maybe it's something we're not doing at all. Maybe it's something regarding the science we need to learn about, getting an early warning system up and running faster, changes to building codes. What should we be doing in a sentence or two, if that's possible?
I think the best thing that we can do to prepare is to improve our seismic monitoring capabilities, because it's obviously going to be beneficial to earthquake early warning, but it goes well beyond that, and the basic data that's collected contributes to the structural engineering, the geotechnical engineering, and just understanding the basic earthquake physics, wave propagation, and source physics. That's something that we really need.
For tsunamis, I think the message that doesn't get out a lot is that the waves are very long-lasting. I don't know if you saw in the historical record, people that got killed in the past tsunamis were killed by 3rd, 4th, or even 8 hours after the initial arrival. So you'll hear tsunami warnings with a particular arrival time. That's the arrival of the first wave. But tsunami waves characteristically go on for at least 2 or 3 days. So you need to listen for the all clear, focus more on that than really when the first waves are really going to come.
A couple of things. One is that there's a damaging tsunami in California every 6 years. These are not the ones like in the northern Japan, but something that causes damage to the coastal environment and the like. So there's a lot more interest in that, and some of these maps that were shown of inundation are now being put in probabilistic forms, and we've had some meetings already on the science side of tsunamis with USGS and others. But there's 2 more workshops that we're going to have, more like what everybody's doing in the tsunami area in the United States, and also then some engineering aspects of this. I think just in watching the news, I hope this last weekend I went down and bought like 4 big crates of water. And all these warnings about having 72 hours worth of food and a disaster recovery plan. We're not going to get 42 minutes of warning to 42 seconds of warning. Our favorite fault is, 100 meters uphill here, so you're going to have something less than a second worth of warning probably. So you better have some water at home. It took some people something like 12 hours to walk home. So, if your significant other lives in San Francisco and you can't get across the Bay Bridge, they're going to be walking most likely around Santa Clara to get home to you in Berkeley. So you need to have some food. The 72 hours, I think, just in terms of what happened in Sendai, is probably a little bit less. Engineering depends on the accuracy or understanding of the earthquakes and what hazard we have to design for, and then we can try to figure out what the risk is, but there's lots of work that's being done in California. NORM is a key player in reassessing the earthquakes we consider in California, but there's also work on the eastern part of the United States, and hopefully starting now for subduction zone events, and so we'll be looking at those kind of things from going from science to the engineering side of this. And I think it's just really this resiliency kind of thing that most people, they still, as I said, think that if they have a building that is code compliant, it is just going to be safe, and they can not worry about that. And I think the picture is not so much of Sendai or things like that, but more of Kobe, where if you go back and look at the damage there, they have a fault that went really close to the downtown area. They had lots of tall buildings that were heavily damaged, lots of buildings that collapsed, 6,000 people plus that were killed and the like, and that's sort of on the line of what we might have here. But there are more isolated, seismically isolated buildings in the city of Sendai, Japan, than in the entire United States. So we have one here on campus. There's Berkeley City Hall has an isolation system, but there are more isolated systems in Sendai than there are in all of the United States. And so I think we will yet have our major disaster that will sort of kick us into not just looking at life safety, but looking at the survivability of institutions and the survivability of our communities.
I will say on the seismic hazard side, trying to quantify the estimates of hazard, subduction models is really a problem for us. We haven't had much effort on that, primarily because that's an Oregon and Washington problem, and they have not taken earthquakes as seriously as we do in California. So I agree with what Steve said. Subduction models are a serious shortcoming for us. My take-home message from the nuclear side is the importance of backup power, and we need to make sure our backup power is really robust, probably beyond the levels that we've now associated with all the other safety-related equipment. If you don't have power, you're really limited in what you can do in emergency response. You can't even be as creative in trying to get through the problem. So I think that's going to be a change that will happen.
Just a quick follow-on to Norm's note, we have new designs for plants that actually don't require power to shut down safely and to remove decay heat, and that's an obvious direction to go in the longer term, moving towards using ambient air as your ultimate heat sink rather than water is something that also would give you greater flexibility. But at a much higher level, I think that these are all questions that fit into a larger context of our societal investment in things that are important, because we see opportunities here to make investments that clearly can be more protective of public health, protect our infrastructure so that it's available after these sorts of events. That fits in a broader context of things such as the current practice of the state of California to disinvest in public education, including the University of California, our ability to provide food and housing and a whole suite of things that our society needs to do. And one of the places where I see some of the best potential is in these ideas of introducing risk-informed design, looking more strictly at what societal performance goals are and giving engineers and scientists the flexibility to identify better solutions to achieve those goals. And so moving away from more prescriptive and deterministic approaches towards more performance-based approaches in terms of how we engineer our infrastructure can make it more affordable and resilient. And if we go in that direction, then I think that we have good prospects of continuing the long-term trend, which is that things have been getting better and safer over time. As long as we don't screw up the climate. Okay, that's a big if, but besides that, everything else seems to be on a pretty good trend.
Let me just emphasize what Steve already touched upon, which is really personal preparedness. So everybody should be prepared. There is probably going to be a large earthquake during our lifetimes here in the Bay Area. And to me, what was most impressive hearing from Japan is how people really rose to the occasion, how people supported each other, helped their neighbors, organized themselves, not waiting for government to come in and fix everything. And I hope we will see similar responses when our next earthquake happens here, that we rise to the occasion that we will be faced with at some point.
Well, on that note, just a quick announcement. We've all been experiencing a range of emotions watching the disaster unfold in Japan, and the Tang Center has some relevant information on the table outside the room. Thank you to the audience for your excellent questions, and let's thank our speakers for being here.